All right, good morning. So let us start. Do you have any questions before we start? Okay, so last time we were discussing 12.6 likelihood ratio test. And so I think now we can put a common message to hypothesis testing. So the common approach to hypothesis testing is by the likelihood ratio. Okay, so the difference is only about when you have simple hypothesis versus composite hypothesis. If the hypotheses are simple, then basically you have what we had before, which is the likelihood ratio, sorry, the likelihood function under the null divided by the likelihood function under the alternative. And, you know, we call this LR, okay? So notice that simple hypothesis means that the likelihood function is completely determined given the hypothesis. So in other words, right, nothing is unknown when we form this ratio, all right? Because do remember that whatever, this right here, the likelihood ratios must be a statistic. In other words, nothing should be left unknown when you form this likelihood ratio. And that's the key to understanding it in the difference between simple and composite hypothesis. With composite hypothesis, remember that when you have a composite hypothesis, then under the under the hypothesis, the distribution may not be completely determined. Therefore, we must take the max. Okay, so the max here allows us to kind of max out all the unknown scenarios. Okay, under the null. So similarly, you take the max. But here, there's a slight difference. Under both hypotheses, like this, and we call this the generalized likelihood ratio. Okay, but one thing to remember is that, you know, these guys are the same. In other words, I mean, okay, they're a little bit different because of this, but more or less, okay, the key idea is the same. In other words, that to decide, right, to decide the null versus the alternative, the key idea is again the same. That is, so key idea, right, is to compare evidence under the null versus under the alternative. All right. I mean, both of these try to express these ideas, all right, just in different setup. So we've done enough here already, and so let's try to explore, okay, the setup where the hypothesis is composite. The main examples we want to keep in mind is something like this. You know, actually there are 3 scenarios, but usually we try to keep the null hypothesis simple. So in other words, there's no max over the null because it's still simple. It's only the alternative that's composite. This is called a two-sided test. The other one would be one-sided. Okay, so these are the main examples we'll look at for the composite hypothesis. All right. So again, I mean, if you want to be more concrete, we can look at the following example. Let's say x1 up to xn iid, let's say exponential lambda. And our null hypothesis is lambda equals to lambda 0. And our alternative is lambda not equal to lambda 0 for some given lambda 0, like 1 or 2. Okay. All right. So maybe, right, maybe let me show you what the generalized likelihood ratio looks like under this example, and then we'll continue with our remarks. So the generalized likelihood ratio would be, right? So first, the likelihood function. So maybe let me do this first. The likelihood function, right, for a value lambda would be what? So will be the product, right? 1 over lambda e to minus xi over lambda. That's for an exponential lambda. So that would be 1 over lambda raised to the n e to minus sum of xi over lambda. All right, so pay attention here, right? So under the null, the point, right? One of the point is that you have to maximize, okay? You have to maximize. So the null, because it's gone already given a value, there's no maximization, but I'll just write it down anyway. The max, right, over all lambda, I guess, under null of this will just be plugging in lambda 0. Because there's only one value. There's only one value. So there's no need to do anything there. Okay. On the other hand, right, the max over everything, right, would be what? So now you see, actually, you see the point of this notation. This means that you take both the scenario under the null and the alternative into account. So what that means, right, is under a null, lambda equal to lambda 0, lambda not equal to lambda 0. So basically, that means the max over everything. Right, so that's the max over everything. And everything here for us, of course, is lambda positive. Why? Because lambda, right, is the rate of the exponential distribution. So lambda cannot be negative. So when you union, right, both scenarios of the null and the alternative, you get everything, meaning lambda positive. So the point is this, right? Naturally, actually, you might feel that you don't need the null here. You want to do something like this, similar to the simple hypothesis case, right? And that actually is fine. In other words, these two are like with or without the null like this. Is basically equivalent setup. But you see that if you don't include like the value lambda 0 here, then the maximization under the alternative, meaning you have to exclude the point lambda 0 out, will be a little bit awkward because, you know, the maximization problem cannot consider the point whether lambda equal to lambda 0 or not. Okay, so that union is just there to kind of make everything convenient. So in other words, right here, it just basically this. And okay, what is this value here? What is this problem here? How do we solve this, or what comes out of this? Can anyone tell me? What comes out of this expression? You have a bigger expression, right? Not smaller, because also, yeah, that's also one of the reason too, because here, right, you take the max over a bigger set, so it cannot be smaller. So a particular feature, right, of the GLR is that the top always is less than or equal to the bottom. Yeah, but yeah, that's one observation, but that's not what I'm asking. What I'm asking is, what is the particular solution that comes out of this? Well, so the answer is this, right? Have we solved this problem before? No, not either, right? Again, my question is very, very specific and simple here, right? So, all right, in case you lose track of things, this is a GR. So I guess you may throw in an extra word ratio, right? You mean just like the other likelihood? Because you throw in the word ratio, I think you meant something else. Yeah. So right, I think, okay, I get it then. What you mean, right, is that it's actually the MLE, right? This is actually the MLE problem that we did, right? This is exactly maximum. Yeah, no worries, because you throw in the word ratio. These things can get confusing. Yeah, I just thought that you refer to ratio, right? Division. It's just likelihood. Yeah, this is the MLE function. Okay, so this is the MLE function, MLE problem, right? That we did before. Remember? So this is a likelihood function, right? When you take the max like this, you're solving for MLE. Except that before, our focus was on the value of lambda that maximized this, right? What was the value of lambda that maximized this? So first of all, replacing it like this is kind of like by definition, because the MLE is whatever that is that maximizes this. Okay, but what is the particular value? Yeah, exactly. So eventually that is. So here actually, right, we only have n. All right. So one remark right here is that with this, the two-sided setup, okay, with the two-sided setup, usually, right, the denominator will end up being an MLE problem. Okay, so one remark is that the case where you have this, then the maximization problem of the likelihood function will be just plugging the MLE. All right. So the MLE will show up in some places like this. And again, right, I mean, that's because the likelihood controls everything. The likelihood function controls all the knowledge, all the evidence we have about, the sample, and that's why it shows up again. All right. But keeping this in mind so that when you see something like this, you don't freeze and you don't, you kind of know how to solve this problem moving forward. But remember that last time I said, right, in general, right, to figure out the max over the null, right, of this, and the max over this of this, we may need to solve, let me just say this, non-trivial optimization problem. Okay, because you have to take the max over some region. Imagine, for example, that suppose the null is like this, theta bigger than or equal to 1. And the alternative is that theta is, I don't know, just for some crazy reason, right, less than 0.5. Okay, then you see that we cannot say something like this. This is out, right? Then we have to take the max over all lambda bigger or equal to 1 of this expression, and whatever that is. And then for here, we have to take the max over all lambda less than or equal to 0.5, whatever that is. Okay, and that, right, if you ask me, I don't know what the solution is unless I look into it and try to solve it. And that is, you know, painful, right? So that is not to say that that situation cannot come out, but in the standard situation like this, because the union is everything, it's worth our while to remember that the MLE, right, is the solution. And so in that sense, right, it's not like we don't have to solve for this problem, but it has been solved. In other words, right, we did our work in the MLE section to solve for this. So we do not have to reinvent the wheel, right? We just plug in our knowledge. Does that make sense? Any question here? All right. So to repeat, right? So in this problem, in this example, our GLR would be, right, the one under the null, which is this, divided by the one under, right, both scenarios. So we got 1 over lambda 0 e to a minus sum of xi over lambda 0 divided by 1 over x bar e to a minus n. Okay. What is our task here? I mean, maybe, right, in case you lose track of things. Suppose this is the setup, right? This is the problem. What are we doing here when we pose this problem? What's our goal? What are we doing? What's the point? What is the point of any hypothesis test? Or what's the goal of any hypothesis test? The goal, right, is to come up with the rejection region. Okay, that's the goal with any hypothesis test. It's the same as, you know, any estimator, right? Any starting out problem of any statistic, right? Any sample is that how do you estimate the parameters? That's really the first question you want to ask. So in a hypothesis test, the question is how to come up with the rejection criterion or rejection region. And so, right, what's the point of proposing the GLR? What's the point of proposing this object? How is this object relevant to this question? The relevance, right, is that you always can do this. In other words, right, that the whole point is this will be the general recipe for any hypothesis test. Like I don't even have to look at this. I can just give you an answer in general like this. Of course, there are many things to discuss, right? Once we know what hypothesis we're in and what setup we have, right? But this is the general direction that we pursue. Is that okay? So now, of course, right, once we have the particular setup like this, then the task is to figure out what GLR is, which is what we're doing here, right? So we figure it out. Then what's the second task? The second task is to figure out what C is. Okay. I mean, actually, that's all you can say now, right? So by the way, again, right, I know that there are a lot of symbols in here. Is this object completely determined? In other words, do I know this object if I observe the sample? Is there anything left unknown? Is this object completely determined? What about lambda 0? So do I know the GLR after I observe the sample? Well, by the way, right, the answer is you should, you must, okay? But just in case you make some mistakes somewhere along the line, and if you, yeah, so is that okay or that's not okay? That's right. I mean, no, absolutely. I agree, right? I just wonder if you're right. Exactly, right? So in fact, right, lambda 0 would just be like, 1 or 2 or something, right? In a particular case, yes. But I just want to make sure because, who knows? I mean, there are too many symbols involved. And you may think that this is like, some weird object we don't know. Yeah, we know this completely. All right. So yeah, that's right. So what I'm trying to say, right, is this is a legit object. Okay, like using this kind of simple reality check, I know that this is legit. I can use it. Okay, but as you see, right, I show you throughout the class that if you're not mindful of the procedure, you may end up slipping in something that is not making sense, right, into your object, into your statistic. So this is fine. So in that sense, right, you can see that this is perfectly fine, right? This rejection region that I'm proposing is perfectly fine. Why? Because I know this, right? This is a statistic. This depends on the sample. Then I just say that, right? I tell to my supervisor that, look, compute this, right? And reject it when it's small. But then what's the next question? What's the next question? At this stage, what's the next question I should ask? I think you're getting there, but what do you try to rephrase that a little bit? And why do we ask that question? Why do we ask that question? Under which cases is the GR less than K? Why do we ask that? Why do we care for that? What are we after when we ask that question? Right. Sort of. So the next question we ask, so actually we're after, right, alpha, we're after type 1 error. Okay, so actually the next question is this, simple. So which one is known? Is alpha, which one is known? Alpha, okay, which one is known? Which one is given in the test setup? Is alpha given or k is given? Correct. So you see, the next question is how to choose k. All right. So again, right, like the path is the same. All right, that's the only one I want to show you, that the idea of the test is the same. It's just the technicality becomes different. That's all. But how to choose k here, right, depends on what. And that now we go back to what Madhav was saying, right? Under what scenarios, or what's the probability of this happening, right? So clearly, and the mundane region is still like this. Right, you can always write that abstractly, right? Because that's true. That's definition. Now, can anyone say what this is? Can anyone say what this is for this object? No, Christine, what I'm asking is what is the particular value, right? Yeah, it's type 1 error. But then now that you know it's type 1 error, right? You remember then the next step is going to be compute this specifically, so we can identify k, right? So in other words, right, the question is, what is the sampling distribution of the GRR? I don't know. Do we know? When you look at this object, do we know what that is? So let me serve you the suspense. Here, we don't know what that is. I mean, by that, I mean this, or I also mean this. I don't know. Look at this, right? I mean, this is 1 over x bar. If you ask me what x bar is, I can say roughly is a gamma because, it's from the exponential. This is also a gamma, but this is 1 over that. And or if you bring it up, that's multiplying, and that's exponential of something. I don't know what that is. Okay. So by the way, again, right, that is not something to despair. It's just the name of the game. In other words, right, I hope that you see the point is the idea of statistics is always the same, and it makes sense intuitively. The technicality is a different question, right? So back into day 1 of this class, I told you probability is super important for this course. It's sort of not important because you needed to understand the statistical ideas, but you needed to execute the statistical idea, all right? So in other words, right, the sampling distribution, you see, if I know it, I can do all the questions I need to do. If I don't know it, then I'm stuck. But I can still pose, right, the approach. So in other words, right, this problem up to here, everything makes sense here, but right, I can't solve this. And let me backtrack, right, and say that I can't solve this analytically, meaning that I don't have a closed form solution for this. We don't have the nice, clean solution I usually give to you on paper. This is where here, right, where I guess practice and other branch of research starts to come into play. I mean, I'll tell you a routine solution here, all right? But like there are many types of solutions that can come up here. You can use numerical approach. You can do simulation to try to see what the value should be. For example, that's one way, all right? Or you can use the next one, which is the asymptotic approach. That's what I'm going to tell you next. But, right, so I just want you to separate, all right, the statistical ideas with the away from the technicality that happens, right? The technicality is that we cannot usually determine this, but the idea, right, that we try to reject this like this is always the same. I mean, it's kind of like makes sense. All right, so question on this. So here we stop, all right? Here we cannot move, we cannot go further. This is it. So for a problem like this, for example, right? Unfortunately, this is where we stop. Question. Okay, so let me put now, right, to recap this, and we'll revisit this again, all right, later. But so the remarks is this, right? First of all, like I said, the LR approach. So by LR here, I do mean, right, GLR approach to, or let me say this, GLR LR approach is the most, right, universal approach to finding, right, rejection region in hypothesis testing. Two, right, in simple hypothesis. So in other words, right, the rejection region will just be this. In simple hypothesis, this C will be most powerful due to Neyman-Pearson. In composite hypothesis, there's no conclusion about the power of C. All right. For many reasons. One of the reasons is actually, you know, when the hypothesis is complex, then there may not be even the most, you know, powerful rejection region. Remember the picture of the power functions we discussed last time, right? There you can have two power functions that one is above the other in some part of the rejection region, but then, you know, below the other in some other parts. So in other words, right, I mean, there's no comparison between them. But here, actually, you have something even a little bit more impressive. You can see example 12.7 in text. I won't go over this example with you. We don't have time for this, but I strongly recommend it. It's actually maybe a little bit hard for you to crack what the message is, you know, what they do there actually, but I strongly recommend that you try to take a look at it. The reason is, you know, it exactly gives you an example where the likelihood ratio approach does not give you the most powerful one. Okay, does not. Clearly, it gives something that is not as powerful as some other rejection region. So in other words, it kind of gives you an example where, you know, this is not the most optimal region to use. Nevertheless, right, there are many reasons why we still stick with this approach. First of all, right, this example is kind of artificial. But second, right, it's kind of hard to see what the general rejection region should look like. So this is still, right, our most kind of go-to approach. But you should keep something like this in mind. 3, okay. The most important question, right? We need to decide so that C has size alpha. All right, that's always the question. And you can see that this leads to simplification of the GLR, this rejection region, into some other region. Where T of X is some stat that we are familiar with. Okay. Or maybe let me say this: one possible approach is to simplify. So what I'm trying to say is this, all right? You always need to find this K so that the region has size alpha. To find this K, you need the sampling distribution of GLR like this, right? But you see, actually, you almost want to say, right, that this depends on this is a function of X bar, which it is, right? You see, this is a function of X bar. But like, there are many things that goes against us in this example, because we are looking at the exponential distribution. So even if we reduce it to X bar, that doesn't mean it's very friendly to work with, because it's gamma. But second, because you reduce it to X bar doesn't mean that you can figure out, right? GR less than or equal to K means X bar is some other region. All right, why? Because the dependence, the structure of X bar here is very complicated. I mean, not very complicated, but it's not as simple as saying, this is a decreasing or increasing function of X bar. You see what I'm trying to say? Because if you bring X bar on top here, right, you see X bar here is increasing in this direction, but decreasing in that direction. So breaking down the region GLR less than or equal to K in terms of X bar here is not a straightforward task, unlike the other ones that we've been doing so far. Is that okay? But basically, right, I'm trying to say this because you will usually see that in elementary statistics, right, you see, basically you say reject when the sample mean is large, reject, you will see the test stat showing up a lot in your elementary statistics. And actually we'll see this approach a lot. We will see a lot of this in chapter 13. All right. I just hope that you understand the message. The message is that we work with some other statistics, okay, as our test statistic, simply because GLR may be very hard to work with. But on the other hand, right, that the connection between these two regions may not be straightforward. In other words, there's no connection at all. So jumping from here to here maybe not like a straightforward task. Then in that case, right, this approach doesn't work. Okay, this approach doesn't work. So alternatively, right, we have the following asymptotic result. Okay, so when n is large, minus 2 natural log of the GLR approach or is approximately has a chi-square with 1 degree of freedom distribution. So, all right, this right here is again another type of mysterious result. Like this one is sort of like up there with the central limit theorem, except that I think the proof here is a little bit more complicated. But what we're saying is, you know, whatever this weird object is, if you take the log of it and you multiply with minus 2, then if n is large, you can say that this is approximately chi-square of 1. How does that help? You see, that exactly helps you to find k here, right? Because if you do this, it will be approximately minus 2 natural log of GLR is bigger or equal to minus 2 natural log of k, which is chi-square of 1, like this. And then from here, right, clearly, if this is equal to alpha, then you got this object to be, you know, if this is equal to alpha, then you got this object to be chi-square of 1 minus alpha as the, you know, the quantile. And then you can solve for k. Is that okay? So that's how you solve for k in this kind of problems. You use the asymptotic. But of course, right, that depends on you having a large sample. If you don't have a large sample, in other words, suppose you have n equals to 3 or 4, then you're stuck. The sampling distribution of the GLR is still unknown. Then you know, you cannot use this result. Does it make sense? Any question? So maybe let me write it here, right? So here, GLR less than or equal to k is this. All right. And so that's all the message I have for this you know, likelihood ratio test. All right. It's a little bit heavy. All right. I get it, because you know, maybe there are a lot of concepts that come together here. But as you move on, if you will take, you know, all the stat courses, I guarantee that you will see likelihood ratio test again, I think. And right, hopefully, right, remembering this can bring more context in for you to see why, you know, you do things the way you do in those courses. All right. Okay. Question? All right. So if not, then let's move on to chapter 13. Okay. Promise, I mean, the material is going to get less heavy now. It will be more straightforward. Hypothesis test, especially at this kind of juncture, is probably the most like heavy material for the whole course. But again, it's a very important concept to discuss. Okay, so chapter 13, tests of significance. Okay, so let me tell you the plan. The plan is I'm going to move very, very quickly through chapter 13. All right. And I want to spend more time on chapter 14, which is regression analysis. Not because I want to teach you regression, that's a different course. I want to show you how regression can be viewed under the lens of this course, because I have a vague feeling that a lot of you view regression as just some computational approach. But anyway, still, right, let's not look ahead of ourselves yet. What is chapter 13 and what do I want to do here? So chapter 13 has these following main points that I will try to very quickly go over. The main points of chapter 13 is exactly to show you right here that, in other words, in a lot of standard tests, what is the test statistic to be used and what is the rejection region? Okay, so standard tests with standard rejection regions. Okay. So, for example, let me just say this. For example, x1 up to xn, IID, normal, mu, sigma square, both unknown. And then you have the null, mu equals to mu 0, the alternative, mu not equal to mu 0. Then the critical region is x bar minus mu naught divided by s divided by square root of n is bigger than or equal to t and minus 1 alpha over 2. Like that. You see how quickly I write it down. It's very, very routine, right? If you can't write down as fast as I can, don't worry. What does it come from? I hope this object is not totally strange to you. This is from the confidence interval, right? So this will feel very much like a repetition of confidence interval in, right, the context of hypothesis testing. That's all. We'll of course, we'll try to kind of bring some light into it in terms of hypothesis testing. But the point is, there's nothing new here. Okay. Actually, there's something new here, but the book doesn't show you it, and you know, there's not much to really go into. Is that not shown, but worth the time for you to really look into, not shown in text. I will talk about a little bit. Is how is this connected with GLR approach? Okay. In other words, right, you will feel strange for the book to spend so much time discussing this kind of thing, and then boom, they go here and they start to tell you this. The point is this, right? That's exactly right here, where the transformation from here to here is possible for this standard kind of test. And that's why I want to show you a little bit, to give you a little bit of idea, right? That the transformation from the GLR rejection region to this is a natural transition. But of course, you do not want to start with the GLR all the time if you know that you're in the familiar context. In other words, if this is the case, you know, everyone would say that's the rejection region, right? They won't pull out the GLR. The GLR is when you enter a new setup where you don't know what to do, right? Same thing as, you know, like in this setup, everyone will say mu hat is X bar. You're not going to pull out the MLE solver and start solving the MLE again, right? You know, you should have your standard tool back and you know what to quote, right? But still, right, it's worth your while to see a little bit of the connection here. Second is some point I don't care about, which is this. This is really about the test of significance. So test of significance, what they say is this. Alpha is given. This is not strange to us. But what they want is this. They want a rejection region, right? They want a rejection region where, let me say this. If, right, you are in C, then we reject. But if we are not in C, then we suspend judgment. So in other words, if we are not in the rejection region, then the conclusion is not to adopt the null, but to say that we do not want to make a judgment here. We don't want to make a conclusion. All right. So let me see here. Somewhere it says in the book, I don't care for this. It's really, you know, kind of a philosophical like kind of statement where, you know, it depends on the setup of the experiment. You want to make the judgment or not, whether the null is true, right? For me, of course, in this class, we care for C and we care for, you know, the power of C, the level of significance, that kind of thing, the size of C, right? We don't care for this kind of judgment. But, you know, like I think it's kind of some point that the text mentions, so I want to bring it up, right? So basically, not rejecting the null may not be equivalent to accepting it, but don't worry about that. In this class, I'm not big on that kind of, you know, statement. All right. So, but the third one actually is important, the idea of the p-value, right? And actually, I think many of you have seen p-value before, right? So, but maybe this is where, if you haven't seen it, I apologize, all right? I don't want to assume, but again, I think in this day and age, everyone has seen p-value at some point. So if you have seen p-value, right, and you have used it, which I think is the case, do you care to say what is it? Like what object it is? Like how do you explain that to a child? Maybe that's too challenging, right? But what is p-value to you? Like what's a concept? Because I do believe the p-value is a vague concept. It's not really a well-defined concept, at least like in the book. First of all, did anyone not hear about p-value? Then I will definitely apologize and I will need to explain p-value to you. But if you have heard of p-value, right, then let's proceed. What is it to you? All right. Okay. Do you see how vague that is? Area from the z-score. What area? And yz? Right? Yes, I know what you're referring to. Absolutely. But two questions then, right? What area? Where do I, what? Actually, that's more important. Why the z-score, I think, right, is another one that probably you recognize, right? It's not definitely the z-score, right? Could be the t, for example, depending on the test. But actually, the more important question for you is what area? And how do you know it? Anyone? So let me say this, right? Probably the most usual way you should remember p-values like this is a magical value, right? That is produced from a test. So given from a test, all right? In other words, if you run R or you run some procedure, your regression, you always have some p-value magically pops up, all right? And you always know that you will reject the test if p-value is less than alpha. I mean, I don't know where equality is drawn. I think, you know, you could, so alpha here is the tolerance level, right? Like, you know, 0.01, 0.05, etc. And you accept the null. Or, you know, if you want to be like number 2, then you suspend judgment. I don't care about that if p is greater than alpha. Okay. That's how I hope that everyone has been using the p-value that way, right? If p-value is small, you reject. If p-value is large, you accept. At least you should remember that much. Okay. But then the question is, how do you compute p-value, right? You see, this class is not about how to use this, right? Because you can just take a different apply stat course and you know, do this procedure. this class asks you how to compute p-value. For example, right, let's go back to here. Let's take this concrete test. What is my p-value? What is my p-value here? So, right, so maybe let's go back to square one. What is p-value? So the book gives this definition, and I think many people adopt this too. And I think it's a good one, except that it kind of is a little bit mysterious. P-value is the smallest alpha level at which we can reject. Okay, that's the most probably common one you'll see at the academic level. So first of all, let's just like kind of unravel this. The smallest alpha level at which we can reject. Then what is going on here? I say if P is less than alpha, then I reject. Are these two statements consistent, or am I making a mistake? Right, you understand? I hope this definition will be, at least somehow understandable to anyone who kind of, seen this alpha discussion in this class before, right? Or if you want, this is type 1 level, right? Type 1 error level. But then the question is, how is that connected with this? Yeah, but again, I'm asking, are you okay with these two statements being equivalent, or do you feel like they don't say the same thing? So let me clarify, right? They do say the same thing. Why? Because here, so don't be right, but no, it is like this, okay? But don't be mystified by this choice of alpha. Like it's the same letter we throw around for many things that have slightly different meanings. So here, alpha here probably should not be meant as a type 1 error, even though it is. But it should be looked at the tolerance level for type 1 error. Okay, it's not type 1 error exactly. It's a tolerance level for type 1 error. In other words, right, if your tolerance, right, if P, right, the level at which you can reject, actually, let's look at this, right? This is probably is clearer. If the level at the lowest level at which you can reject, right, is higher than your tolerance level, then you cannot reject here, right? Because you require to go lower than P. Because tolerance level means you do not want you need the alpha to go below that, right? You want your type 1 error to be below alpha. But on the other hand, p-value is the smallest at which you can reject. So if you require your type 1 error to be even below alpha, then you cannot do that because p is the lowest you can reject. So you must accept. Is that okay? That's why it's consistent. Conversely, same thing here, right? P is the lowest you can reject. Alpha is your tolerant. I mean, in other words, you say you want your type 1 error to be below alpha, but because this is the lowest type 1 error you can which you can reject, which gives you some room here. So yes, right, you definitely can reject here because your type 1 error, right, will be below alpha, right? This is the smallest alpha level at which you can reject. Is that okay? So I want to make sure you understand that these two statements No, it's fine. It's exactly this alpha right here. I also got confused. That's why I want to make sure, right, that you understand these two concepts are consistent. This right here should not be understood as a type 1 error, but it should be understood as a tolerance of type 1 error, okay? That's the level that we require our type 1 error to be below. Anyway, right, still I find this definition a bit mysterious, which is fine. You should keep that in mind. The definition that you actually will find in the internet, or actually the more down to earth version is this: p-value is the probability that we observe more extreme values than our test step. Okay, I think this one actually is quite intuitive and it can be easy to work with. There's some trouble with it, but we can work with it. For example, let's take a look at that one: x1 up to xn, IID, normal mu sigma square. The null is mu equal to mu 0. The alternative, mu not equal to mu 0. I'll test that, right, is this little t right here, which is x bar minus mu naught divided by s over root n, right, absolute value. So actually, you know what? Let me do this. Let me throw away the absolute value like this. This is our tester. So can you, okay, first of all, I'm not sure. Let me backtrack, right? Let me not jump too quickly. First of all, do you see that this is a very reasonable test set for this hypothesis? Why? What are we testing, right? We're testing whether the true mean is at mu naught or not at mu naught, right? The true mean, the true population mean is at this level or not at this level. Okay, so what do? It's very reasonable then to compare, right, the sample mean with mu naught, because the sample mean is a representative of the true mean, right? So in other words, intuitively, right, if the sample mean is close to mu naught, you go with this. If the sample mean is far from mu naught, you go with this. Except there's a little hiccup, right? The hiccup is close or far. It's a bit subjective. Subjective means what? Close or far is driven by how variable, right? How widespread your original distribution is. Also, close or far also has to do with how tight the X bar is, right? Tight means the more sample, right? The more X bar is close to the true mean, whatever that is. Therefore, right, you need to compensate for the widespreadness of the original population, which is sigma squared, but you don't know it, so you try S. And then, right, you also need to compensate for the tightness of the calculation, so you do divide by this. But of course, you know where this comes from, right? This is just a variance of the standard deviation X bar anyway. So this is the normalization step, right? And so after you normalize, then you see that this is the proper object to compare, right? And so the rejection criterion is if this is large enough, right? Why? Because if this is large enough, that means X bar is sufficiently far away from mu naught, right? Are you okay with the intuition here? And how large is large enough? Well, that's where our alpha comes in. How large is large enough? Well, right, then you say, well, I need alpha to be probability, right, of t bigger than or equal to k given h naught. So, and solve for k. But of course, right, under the null, t here has a tn minus 1 distribution. Sorry, right, absolute value. That means k is my tn minus 1 alpha over 2 score. Are we okay here on how this procedure works out? I did go a little bit fast there, but because I think we have seen this in confidence interval, so I assume you're familiar with it. Any point you want me to elaborate? All right, so I mean, pay attention, right? This is a random variable, right? This is a score, this is percentile, this is a number, all right? It's just the notation, it's all we use all the time, okay? But now let's go back to my question then, right? So this is the approach. This is the non-p-value approach. Okay, non-p-value approach. Meaning what? Meaning that you say, right? You say that right here. So basically, you say this. You reject if this is true. Okay, you reject if this is true. That's exactly what we wrote down there. Again, if you read a standard text in stat, they will say this is non-desirable, right? You know why it's non-desirable? Why is this approach non-desirable, or not ideal in practice or in publication or whatever? I mean, frankly speaking, I haven't seen people making a big fuss out of that, but probably because they don't use this approach anyway. This approach is non-desirable because the experimenter gets to choose the alpha, not the audience. I think, at least that's the conventional explanation, right? Because I mean, when you come up with this rejection region, you choose the alpha, you the experimenter, all right? Now, suppose I go along and I hear that you reject about this experiment. Let's say you say that the vaccine for COVID-19, right? You reject, meaning you say it's effective. I'm curious what level of alpha you're using, right? It may or may not be reported, etc. I don't know, I think. And so it's probably better to report the p-value and then let the reader, right, audience, whatever, their own decision. With their choice of alpha. Is that okay? So in other words, right, you have exactly the same setup. You have exactly the same test stat. That cannot be changed, right? Otherwise, you fabricate the experiment. Everything is up to his the same, except that instead of saying, reporting whether you reject or accept, you say that here's my p-value. Okay, and which again, I assume that, right, that's what you guys always see when you run some procedure on R or whatever. And then, right, imagine then, right, you have the p-value, then an audience comes along who reads your experiment and they say, okay, 0.05 is good enough for me. Then with your p-value, I will reject the norm, right, for my preference. But another one come along who has a stricter alpha, who say, no, right, from my standard, I need to go with 0.01, then, in your experiment, I cannot reject the norm. Is that okay? So that's the taste of the p-value, okay? But again, right, that the point of this course, or at least the point I want to convey to you is, it's not about reporting the p-value, because, not how to use it, because, software can do that for you. The curiosity is how to compute the p-value for yourself, right? You take the step of designer here. Suppose you come up with this experiment, and you know that your boss asks you to output a p-value, okay? Not the rejection or acceptance. How do you compute the p-value here? So a lot of times, okay, this statement will give you the guide. All right. So this is our test stat. All right. So it's a little bit confusing here. In this approach, the test stat is treated as a random variable. Okay. In this approach, the test stat is treated as a random variable. In the p-value approach, the test stat is treated as a constant. Okay, like this. Okay, but first of all, right, what does it mean to be more extreme than my test stat? Well, again, right, go back to the spirit of the hypothesis test. I will reject, right? I will reject. I form this test stat with the intention that this I will reject. I would go with the alternative if this is too large or too small. I mean, too positive or too negative, right? That explains the absolute value. Agree? Because if it's too positive, that means this is very big compared with this. If it's too negative, that means this is very small compared with this, right? So in other words, two more extreme than my test stat here takes on two meanings or two possible cases, right? Again, because of the two-sided test. So in other words, p-value in this is going to be probability that the t random variable in absolute value is bigger than or equal to the absolute value of my t. I don't know. Are you okay with this? So here, right, this is treated as a fixed number, not as a random variable. This is the random variable right here. In this calculation, this is treated as a, oh, sorry. So then there's no under no here. It's just this. This is treated as a random variable here. Okay. And why do I form a p-value like this? Again, because I know, right? This is again tn minus 1 because I know that t is a tn minus 1 under the norm. Okay. So in other words, right, this is your p-value and that's it. In other words, you go ahead and you compute, and I think maybe you have done this in an elementary stat course, that you have concrete numbers here, whatever they are. You calculate whatever this is as a concrete number, then you go in and you look up your t-table. All right, you look up the t-table where, I mean, depends on whether it's negative or positive, right? Let's say it's negative. Then you look up the t-table where it's less than this value, and you multiply that by 2, because you know the t distribution is symmetric, and that's it. Is that okay? Any question on this? Okay, so I hope that that was clear. Then the next one will be variations of this question, right? So we still have x1 up to xn IID, normal mu sigma square, both unknown. The mu equals to mu naught. But now the alternative is the alternative mu bigger than mu naught. Okay. So what is my test stat? My test stat should still be the same. In other words, it should still be this. What will be my rejection region? And what will be my p-value? Can anyone tell me? So this is rejection region, right? Definitely of size alpha. That's always the implication. What is the rejection region in this case? So to think about, right? Remember, what is the distribution of this guy? It should be Tn minus 1 under the norm. When do we reject? The alternative says, right, because x bar is the estimated for mu, we should reject when this guy is very positive, right? Very positive. In other words, you should reject when t is bigger than Tn minus 1 alpha. Is that okay? And your p-value will be the probability that Tn minus 1 is bigger than t. Are you confused yet, or are you okay? Again, right, do remember, we treat this as a random variable in this case. We treat this as a fixed number in this case. Yeah, okay, so how to say this, right, Christine? First of all, right, I hope you understand the approaches, right, between the difference between the rejection region approach, which is what we've been doing so far, and the p-value approach. Okay, they're kind of equivalent, but they have different flavors. The rejection region approach just kind of asks you to get out that value that at which you cut off, at which you reject. Okay, that little k right here. So you have to, right here, you have to go into the context of what are these hypotheses, especially this guy right here, to see what they're telling you. Okay, here, right, what it's telling you is if the sample mean is sufficiently different, you don't care if it's positively different or negatively different, then you reject. Okay, that means you reject this when the absolute value of this is large enough. Okay, but then how large is large enough? Well, because of the t distribution, right, because of the Tn minus 1 distribution, large enough here is the quantile with alpha over 2. Why alpha over 2? Because it's two-sided, right? This is absolute value. So it's 2 times the probability with the absolute value times k, bigger than equal to k. Here, right, basically what I'm telling you here is a one-sided test, right? This is a one-sided test. Okay, but it's the same intuition. This is my test stat. But now, right, I will only reject if this is large in the positive direction, because this is what I'm caring about. In other words, right, I will reject when this right here is large enough, but large enough here is this. Notice this is only alpha, not alpha over 2, because I have one side. P-value, right, is the opposite. P-value asks me, when do I observe more extreme value than my test stat? This is my test stat, right? So this is a number. So I will reject, oh, sorry, the probability, right, of observing more extreme value than my test stat is a probability that the Tn minus 1 distribution is bigger than that value. I mean, it's sort of the same kind of picture, but so this is a t distribution, right? So just give me a moment. The first question, right, says that this is Tn minus 1 alpha. Okay. And the first question say that search for the t value. If the t value is here, then you don't reject. If the t value is here, then you reject. Okay, this is rejection region approach. For the second one, it says this. Here's your t value. Okay, this is still Tn minus 1 curve. What is this area? and that's P. You see, it kind of both points to the same region, except that the role gets switched. One is you fix this and you search where T is. Second is you fix T and you calculate the probability you're above T. Okay, but it's equivalent because it kind of points to the same area. All right. Okay, I'll let everyone go. If you still have questions, I'll be happy to answer. If not, we'll continue on Friday. You too. Thank you. You too.